discussion today. So today we are going to cover the last algorithm from unit number 5, and that is the back propagation algorithm. So in the last class we have gone through the multi-layer neural network, and we have seen why there is a need to have multi-layer networks. So we know that a single layer perceptron is a very basic neural unit. Perceptron, which is a single layer neural unit, it is very fundamental neural unit, and it is typically meant for finding out the decision boundaries. Those are linear. So perceptrons work well whenever we are having linearly separable data, and it is possible for us to come up with the linear decision boundaries. So if I'm having such kind of a data set, then I may come up with a linear decision boundary with perceptron. Also, we have seen that we may use the activation function that may be a thresholding function or a sigmoid function. So in the last class, we have gone through the sigmoid neuron also, which uses the sigmoid activation function. But the limitation of perceptron is, as I mentioned, it is not possible for us to learn complex nonlinear functions using a single layer perceptron. And that is the reason why we come up with a multi-layer neural network. So perceptrons are also having the learning algorithms available, but still it is not possible to model some complex non-linear functions using single perceptrons. Say for example, we have gone through few Boolean functions also. So if I am having the AND function, or if I am having the OR function, then these functions can be learned by making use of a perceptron, and we have seen how. But if I am having a function like XOR function, Boolean XOR function, so how this Boolean XOR function looks like, or if I say that I am having two inputs, say x1 and x2, then the truth table for Boolean XOR is like, if I am having the input 0, 0, then I'll be having output as 0. If the input is 0, 1, then I'll be having the output as 1. If it is 1, 0, then also I'll be having the output as 1. And if it is 1, 1, then I'll be having the output 0. So if I try to plot this x1, x2 onto this two-dimensional space, then see here, this is my point, say 0, 0. Suppose here it is 1 and here it is 1. So the point 1, 1 would be, say here. So this is 1, 1. Right? And let us assume that 0, 1 is this point and 1, 0 is this point. So see here, this 0, 0 and 1, 1, 0, 0 and 1, 1, these blue points, these belong to negative class, class 0. And these 2 points 0, 1 and 1, 0, these belong to positive class, class 1. So if we look at this particular problem, it is not possible for us to come up with a linear decision boundary. So no linear decision boundary to segregate these samples. if we are talking about this Boolean XOR function. So using a single perceptron, it is not possible to get the solution for this function XOR, exclusive OR function. So this is just one example. So this function cannot be learned by making use of a single perceptron. And there are lots of such functions, those cannot be learned by making use of a single perceptron. And to learn such kind of complex nonlinear functions, we need to make use of multi-layer neural network. Right? So we have seen how the multi-layer neural network looks like. Right? So the multi-layer neural network looks like this. Here we are having input layer, we are having one or more hidden layers, and we are having the output layer. Right? So in hidden layer we may have more than one neurons. In output layer also we may have more than one neurons. So if we go with such kind of architecture of a neural network, then it is possible for us to learn non-linear functions. Right? And to learn such kind of non-linear functions using multi-layer neural networks, obviously we need some learning algorithm. And that learning algorithm is nothing but the back propagation algorithm. So this algorithm we are going to learn in this session, back propagation algorithm, that is meant for learning multi-layer neural networks. Is that okay? Yes? May I proceed?
Yes, ma'am.
Right. So see here what actually we mean by back propagation. So this is one multi-layer neural network, right? So what we are having here right now, if you look at this neural network, we are having here, this is my input layer, right? I am having one hidden layer and I am having one output layer, right? So this is two-layer network, two-layer. So we are not counting actually this input layer, or even though we count this input layer, we say that this is layer 0. This hidden layer is layer 1 and this output layer is layer 2. So meaning we are having two layer. This is two-layer neural network which has one hidden layer and one output layer. So we are having here, these are the inputs x1, x2 up to xn. These are our inputs. So every input, so this is fully connected network, meaning every input is connected to every neuron in hidden layer. So these are the neurons in hidden layer. So this input x1 is connected to every hidden unit, right? This x2 is also connected to every hidden unit and so on. So associated with all those connections from input to the hidden neurons, we are having associated some weight, right? Now we are in this particular example, we are having only one hidden layer. It may happen that if we go for more complex networks, we may have more than one hidden layers, right? Now, in this example, we are having one hidden layer and this hidden layer is connected to the output layer. In output layer, I may have one or more neurons. So every hidden layer neuron and every output layer neuron is also connected. So we are having the connection between every hidden neuron and every output layer neuron, right? So once again, with these connections, we are having some weights associated. So input signal goes from left to right, from input to output, right? So sometimes we may say that it is a forward propagation. So input signal goes from the input layer to the output layer, and the error signal goes from output layer to input layer, right? So this is in backward direction. Error signal always flows in backward direction, whereas this input signal flows in forward direction. Now, we know that we are having some training data with us, and that training data is being used to learn the network as usual, right? So the training data is of the form x comma y. So x is my input feature vector and y is the associated label that I know, right? So output is known for training data because this is a supervised architecture, right? So we know the input and we know the actual output from the training data set. So the error can be computed at the output layer because we know the actual output y, correct? And we know the observed output from this network, right? So it is possible for us to compute the error at the output layer. So error in actual output and observed output can be computed at the output layer. So error is known here, but we do not know the actual intermediate outputs at hidden layer. Those are not known, right? So how I can find out the error at hidden layer? That is the question. Because the error can be computed at the output layer because I know the actual output and I can find out the observed output of the network. So error can be computed at the output layer only. But if I want to find out what is the error at hidden layer, then it is not possible for me to compute the error directly at the hidden layer. Are you getting me? Are you getting me?
Yes, ma'am.
Right. So, in fact, see here, the output of this hidden neuron is given as input to my output layer. Output of hidden layer is presented as input to the output layer. So whatever are the outputs of my hidden layer, those are contributing in this error indirectly. So we have computed this error at the output layer, but whatever is the error in hidden layer, that error is contributing in this final error. So what we can do is, if it is not possible to compute the error at hidden layers, what we can do is, error at output layer can be back propagated to the previous layer. So this error that we are computing here at output layer, that can be back propagated to the hidden layer or the previous layer. So if I am having few more hidden layers, error at this point can be back propagated and so on. Right? So ultimately, whenever we say that we want to learn this neural network, meaning we want to learn the weights and the biases, right? So ultimately, in our learning algorithm, what we want to do is we want to learn these weights, right? So initially, whenever I am presenting the training sample, I will be computing the error. That error gets back propagated to the intermediate layers, right? And if that error is not minimum, then we are supposed to modify our initial weights. Once again, we are going to follow the same procedure, and we have seen in the earlier class how we can make use of gradient descent to learn the perceptron. The similar concept we are making use of here. So here also we'll be making use of gradient descent, right? So we need to minimize the error that we are having. So every time we are computing the error, we are back propagating the error, right? If that error is not minimum, then the process continues till we reach to the minimum error. And once we reach to the minimum error, then we will say that our model is trained and it can be used for prediction. So see here, this process that I described right now. Suppose this is my network, neural network, right? So what I'll be doing? I'm having associated the weights between all the neurons, right? At the output layer, I'll be computing initially the error. If the error is minimum, then I may say that my model is ready to make prediction. But if the error is not minimum, then what I need to do? I need to update the parameters. What are the parameters here in our case? The parameters are the weights. So I am going to update the parameters. So after updating the parameters, once again I will be computing the error. Once again I will be finding out whether the error is minimum. If no, once again I will be modifying the weights and the process will continue till I get the minimum error. So once I get the minimum error, I will say that my model is ready to make prediction. So while calculating the error, what we mean by error? By making use of this concept of error, we find how far is our model output from the actual output. So simply we try to find out the error between the actual output and the observed output. That is the error, right? Whenever we say that minimum error, we check whether the error is minimized or not. So we make use of gradient descent to reach to the minimum, right? Now, if the error is not minimum, then what we are supposed to do? We need to modify the parameters. So here our parameters are nothing but the weights and biases. So after updating those weights, once again we compute the error and we check whether it has reached to the minimum, right? And this process continues. So once it has reached, so we know this plot. So once it has reached to the minima, then we say that our model is trained and our model is ready to make the prediction. So once our model is ready, we give the test samples to the model and then our model predicts the output by making use of the finalized weights. So this is what the in general process is, right? So Let's go through now the back propagation algorithm. So I hope you must have understood the process of back propagation. Simply what we are trying to do is, here the error is being computed, as there is no means to compute the error at hidden layer. What we can do is, we can back propagate this error to the previous layer. Once again, we can back propagate this error to the previous layer, and so on. Right? So back propagating error helps us to modify these weights. Okay? So let us go to the algorithm now. I hope the concept is clear now. We are not going into the derivations, mathematical derivations. Simply, we are going to look at the steps in back propagation algorithm. And I hope you must have understood the concept of back propagation. If you have any kind of doubt, please let me know. Yes. Any doubt?
No, ma'am.
Right. So let us go through now the algorithm, back propagation algorithm for multi-layer neural network. So here also our input is the training data set D, which consists of the training samples of the form x comma y, where x is a feature vector and y is my target output. Right? The first step is, we need to initialize all the weights to some small random number. So there are so many weights now. So what are those weights? Weight is associated with every connection. Right? So all those weights need to be initialized using some small random numbers. Also, we need to make use of the learning rate eta. So that learning rate eta also need to be initialized. Now, this is the iterative process as I mentioned. So while we are not reaching to the minima, that means while there is no convergence, we are going to iterate through. So what we are going to do is, we are going to pick up every sample from our training data set. So for each training example, do what we are going to do. Number one, input the training example to the network and compute the network outputs. So see here, this capital X is my feature vector. So this capital X comprises of some values x1, x2, x3, so on up to xn. So this is my feature vector. So whenever I am saying that I am inputting a training example to the network, meaning if this is the first sample x1, then whichever are those features are input to my neural network. Right? So these values of the features are the actual inputs. Right? So input the training example to the network and compute the network outputs. So how I am going to compute this output? It is really very simple. What we are supposed to do, we are having here, say for example, one hidden layer. And let us assume that these hidden layers are sigmoid units. So we are making use of a sigmoid function as activation function. So what will happen? See here, suppose this weight is, this is my first input and this is first hidden unit. So let us assume that we are abbreviating this as W11. Right? So weight associated with this is W12. Weight associated with this is W13 and so on. So initially we are having some random values assigned to all those weights. So for this hidden unit, what are the inputs? I am having W11, then I am having W21, I am having W13, suppose this is ith input, so I1, Wi1, okay, and this is suppose Wn1. So for this sigmoid unit, what I am having as the inputs, I am having x1 multiplied with this W11, x1 into this W11, correct? Now what is the other input, x2 with the weight W21, so I'll be having plus x2 into W21 and so on. So it is summation of xi wi. So weights are associated with the connections, right? So for this unit, my input becomes x1 w1 plus x2 w2 plus x3 w3 and so on. Are you getting me?
Yes, ma'am.
Right. So here we are using the sigmoid function. So this sigmoid function, we know the sigmoid function. So how our sigmoid function looks like? This is 0, 1, this is 0.5. So our sigmoid function looks like this. So this is my activation function, right? And see, this is say 0.5. So this sigmoid function will produce the output. So what is the input for this sigmoid function? This summation. And based on this, this sigmoid function will give me the output which is in the range 0 to 1. So that output I'll be getting at this point, at this sigmoid, right? Now, this will become, so once again, I'll be having the weight associated with this. So if this is my first hidden neuron and this is my output neuron O1, suppose let us assume, then this weight, let us denote it as WH1O1. So weight for the link from hidden unit 1 to the output unit 1. So this is the weight. So this is second hidden neuron. So this link carries the weight W, say H2O1 and so on. Right? Just for understanding, I am abbreviating like this. Okay. So these are now the weights associated with these links. And associated with every neuron, I am having now some output, and that output is produced by this sigmoid function. So this summation xi wi is the input for this neuron, and this sigmoid function will produce some output that is in the range 0 to 1. So I am having available now the output here, intermediate output for this hidden layer neurons. So this output becomes now the input for the output neuron, right? So whatever is this input multiplied by this weight. Once again, I'll be having the summation over here. This input now and the associated weight. And once again, my activation function is the sigmoid function. So this sigmoid function once again will produce some output at every output layer. Okay. Now, what I will do, I know actual output. I am having now the observed output. So I'll be computing the error. Right? And that error is back propagated to the hidden layer. Then it is back propagated to the input layer. And these weights are being updated if required. So let us proceed now with our algorithm. The second step in our algorithm says that for each output unit case. So we have presented the training examples to the network, right? And we are computing the outputs. So now you know how the outputs are being computed. Now, for each output unit K, that means this unit. For each output unit K, we are computing this del K as OK into 1 minus OK into YK minus OK. And for each hidden unit H, we are computing this del H as OH into 1 minus OH summation over K belongs to outputs WHK del K. So del K is computed for every output neuron. That del K is being used while computing this del H along with these weights. Going into the derivations. Now, once we have computed these quantities, what we are going to do is we are going to update the network weight. So all those weights are being updated. So how I am going to update those weights? Wij gets updated, every weight gets updated as Wij plus delta Wij. So what is this delta Wij? This delta Wij is equal to eta times del j into xij. Eta times del j into xij. Right? So this is my small change in the weight. So this small change in the weight is being updated in the old weight, and I am coming up with the new weight. So now what happens is this process is repeated. For each training example, actually we are doing this, right? And we are going to iterate through till we get the minimum error, right? So convergence means we are iterating till it reaches to the minimum error. If the error is not minimum, then we are going to follow this process iteratively and we are going to modify these weights, right? So this is actually the overall back propagation algorithm. So if you are interested, I'll solve one problem for you so that you can understand how actually this algorithm works. So may I go with one example?